In this video, we consider an unpaired two-sample problem, but this time when the samples are small. So we have data that we're going to show you on the screen right now. We have 8 samples of carpeted hospital rooms and 8 samples of uncarpeted hospital rooms. We were counting the number of bacteria samples that are found per room. And the question is basically, does it appear that the carpeted rooms have more bacteria than the uncarpeted rooms? Okay, so we have a unpaired two sample problem, but this time the samples are small, only eight per sample. So we'll use the procedure of hypothesis testing for this. The null hypothesis will be that the two means are equal, that the difference between the two bacteria levels are attributable to chance, whereas the alternative hypothesis will dictate that the first one is bigger than the second. So if the first one is bigger than the second, that means the difference is greater than 0. Okay, we will use the test statistic t, and the test statistic t will be equal to the first sample average minus the second sample average, so the observed difference, minus the expected difference, divided by the standard error for the difference. And the standard error for the difference is obtained by using the sample standard deviations, s1 squared over n sub 1 plus s2 squared over n sub 2. Okay, so we'll use Excel to facilitate these calculations. First off, let's figure out the summary statistics for the carpeted and the uncarpeted rooms. So the average of the carpeted rooms works out to be 11.2, and the standard deviation of the carpeted rooms works out to be 2.677. And just fill down the pattern. The uncarpeted rooms, that average is 9.8, while the standard deviation of the uncarpeted rooms works out to be 3.21. So first off, let's get the standard error for the difference. So that'll be equal to the square root of the first standard deviation squared divided by the sample size of 8 plus the second standard deviation squared divided by the sample size of 8, so 1.47786. And this leads to the t-value of the first mean minus the second mean minus 0, so the observed difference minus the expected difference, divided by the standard error, so I get 0.95577. So that is our t-value. The next step is to figure out the number of degrees of freedom. The number of degrees of freedom is actually a fairly hairy formula, which you now see on the screen. So we have a fairly complicated formula for getting the number of degrees of freedom when doing a unpaired two-sample t-test. There's no shortcuts, so let's go ahead and figure this out. So see if we can get this on one screen. So the number of degrees of freedom will be equal to the first standard deviation. Let me slide this over so the whole formula should fit. The first standard deviation squared divided by the sample size plus the second standard deviation squared divided by that sample size, whole thing squared, divided by 1 over 7 times first standard deviation squared over 8, whole thing squared, plus 1 minus the second sample size minus 1, 1 over the second sample size minus 1, times the second standard deviation squared over 8, whole thing squared. So hopefully I have typed that in correctly in Excel to match the formula for the number of degrees of freedom that's on the screen above. And so that works out to be equal to 13.56, and we round down to the nearest integer to be 13. I'll point in parenthetically, that's the formula that we'll be using in this class. However, there's not universal agreement about the number of degrees of freedom that should be used in a test like this, and I'll defer discussion about that to a future course in statistics. But that's the formula we'll use in this class, but there's far from universal agreement about this. if you look at different statistics textbooks, you might see a different definition for the number of degrees of freedom in a test like this. Okay, so we have that's number of degrees of freedom, and we round down to be 13. Okay, so we can now continue the procedure. We have two things that we can do. We can do the critical value, which works out to be t dot inv of 0.95 with 13 degrees of freedom. So using Excel, we want 5% of the area to lie to the right so that 95% of the area lies to the left. So using Excel 2010, we get this to be 1.77093. Clearly, our t value is less than the critical value, and so the decision will be to retain the null hypothesis. The second way of doing this is by figuring out the p-value, and this will be equal to, well, what I'm about to type is incorrect, t.dist of the t-value with 13 degrees of freedom, and we want it to be cumulative. However, I want the area to the right of this number, not the area to the left, and so I want 1 minus this. So the p-value works out to be 17.8%. That's bigger than our default value of 5%, and so our decision again will be to retain the null hypothesis. So let me draw the picture on the screen so we can see exactly what we just did. The first method with the critical value, we found a critical value of 1.77093, which means that the area to the right that's shaded is 5%. And so the decision would be to reject the null hypothesis on this side for abnormal values of the test statistic, while the decision would be to retain the null hypothesis on the other side. Okay, that's one way of proceeding. The second way of proceeding is by looking at the value of t, which was worked out to be 0.95577. That falls in the area where I retain. And then the p-value would correspond to the area in green that's being shaded. And that area in green worked out to be 0.178. Clearly that is bigger than 0.05. I shaded over the red region, and so that's bigger than alpha, so my decision again is to retain the null hypothesis. So, concluding, we retain the null hypothesis. There is not enough evidence yet to conclude that the carpeted rooms have higher bacteria levels. And we don't have enough evidence yet because we only took a very small sample of size 8 apiece. Perhaps if I took a larger sample, I would detect higher bacteria levels. That, of course, has been detected so that when you go to the hospital, we have tiled floors in the patient's rooms as opposed to carpeted rooms.